So this first slide is, in some sense, giving the theme of my talk this evening. Whenever we remember Ramanujan, three things come most vividly to mind. Ramanujan, one, Ramanujan was a truly great mathematician. Two, Ramanujan's life story is inspiring. And three, Ramanujan's life and work give credible support to our belief in the universality of truth. So let's move to the next slide. Or can I? Oh, perfect. So if we had to choose one word to characterize the impact of Ramanujan's work, it would be surprise. This is perhaps most evident in Hardy's response to the two formulas that you see on the screen. So these are truly quite surprising results. And Hardy commented on them as follows. I had never seen anything in the least like them before. A single look at them is enough to show they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have the imagination to invent them. Finally, you must remember that I knew nothing whatever about Ramanujan and had to think of every possibility. The writer must be completely honest, because great mathematicians are commoner than thieves or humbugs of such incredible skill. So, yes. So, in this letter that contained the two formulas you saw, it turns out that these formulas are corollaries, as G.N. Watson showed, of what are now called the Rogers-Ramanujan identities, and you see both these series and products here on the screen. The first series, the exponents in the numerator, 1, 4, 9, etc., these are the perfect squares. In the first product, the exponents go 1, 4, 6, 9, etc. Those are the numbers congruent to 1 or 4 mod 5. In the second series, you see 2, 6, 12. These are the numbers of the form n squared plus n. And in the second product, you see 2, 3, 7, 8, etc. These are the numbers congruent to 2, 3, and 5 mod 8. The reason that these cause such a stir and cause such difficulty for, I'm trying to move to number 2, slide 3, yes, there we are. The reason that these cause such difficulty for Hardy in studying them was the fact that the formula that you see on the screen here is a formula that looks very much like the two Rogers-Ramanujan identities. The exponents on Q on the numerator here are the triangular numbers n squared plus n over 2. The exponents in the product are just the odd numbers. And the reason that Hardy was so dumbfounded by it is this formula, which goes back to Euler, is easy to prove, whereas the Rogers-Ramanujan identities are very hard to prove. Hardy sent these to, not only showed them to Littlewood, but sent them to McMahon, sent them to Perron in Germany, and nobody could prove them. So Hardy, in his book on Ramanujan, has the following quotation, which tells what the history is. He says these formulas have a very curious history. They were first found in 1894 by Rogers, a mathematician of great talent, but comparatively little reputation, now remembered mainly from Ramanujan's rediscovery of his work. Rogers was a fine analyst whose gifts were on a smaller scale, not unlike Ramanujan's. But no one paid much attention to anything he did, and in particular, the paper in which he proved these formulas was quite neglected. Ramanujan discovered the formulas sometimes before 1913. He had then no proof and knew that he had none, and none of the mathematicians to whom I communicated them could find one. They are stated without proof in the second volume of McMahon's combinatory analysis. The mystery was solved trebly in 1917. In that year, Ramanujan, looking through old volumes of the Proceedings of the London Math Society, came accidentally across Roger's paper. I can remember very well Ramanujan's surprise and the admiration he expressed for Roger's work. A correspondence followed, in the course of which Rogers was led to a considerable simplification of his original proof, and about the same time Schur, who was then cut off from England by the war, rediscovered the identities again. Schur published two proofs, one of which is combinatorial and quite unlike any of the others known. Indeed, Hardy describes the Rogers-Ramanujan as perhaps the most beautiful identities that Ramanujan discovered. However, he acknowledges that Rogers has priority in having them discovered them 20 years before. So when Hardy tries to give the most beautiful formula that Ramanujan found, he gave the one you see on the screen here, which is where P of n denotes the number of partitions of n, the number of ways of writing n as sums of positive integers. And the point here is that if you pick every fifth value starting at P of 4, so P of 9, there should be an x times a P of 9, an x squared times P of 14, then there would be an x cubed times P of 19, etc. This expression is equal to this infinite product that you see on the right with 5 as the coefficient, meaning that every value of P of 5n plus 4 is divisible by 5. Among the really great discoveries that occur in Ramanujan's work, one must cite the Mach theta functions. You'll forgive me for having this expression vertically on the screen as you see it, but basically this is one of the generalizations of the Mach theta functions and one of the results for it that Ramanujan actually found and that appears in his Lost Notebook. And the Lost Notebook, as many of you may understand, is something that I have spent many decades of my life studying. This is the document that Ramanujan prepared in the last year of his life, 1919 and 1920, and which contains results like you see on the next slide, which are incomprehensible. So there are many aspects of Ramanujan's work that you find that he presented that we just don't know what are. They seem to be related to the Mach theta functions, but they get even more, if we move to the next slide, we see that they get even more chaotic and surprising. Indeed, you see right in the middle of the screen here, there's a horizontal line, and then there is this expression that is 1 minus q squared plus q to the 5th plus q to the 7th. This is Euler's pentagonal number series, which Ramanujan knew well and which played such a substantial role in much of his research. And one of the things that I thought I would highlight tonight is one aspect of this series. The exponents 1, 2, 5, 7, 12, 15, 22, etc. that you see in this series are what are called the pentagonal numbers. And Euler himself observed that they play a very substantial role in calculating and studying the partition function P of n. So I wanted, as the component related to the Mach theta functions, to describe for you one of the more recent things that have been discovered, indeed work that I've done jointly with Mircea Mrka, and that if we can go to the next slide, the work on the fifth order Mach theta functions actually owes much to Shanks' truncated formula, which is at the bottom of the screen here. You see that these exponents in the sum on the left-hand side, 1 plus, etc., these are the pentagonal numbers. And what Shanks has done is to identify these with the sum on the right, so that when the little n tends to infinity, this becomes the classical theorem of Euler. And this sort of thing arose in much of the work of Ramanujan. So the story that I want to tell, starting with the next slide, so if I can move to the slide after this. Yes, that's it. Recently, this story began a new chapter, and the chapter went as follows. Mircea Mărcă, who is Romanian, was working on combinatorial algorithmic developments for the partition, representing partitions, and he wanted to prove the inequality that you see in the middle of the screen here. Namely, just the first four expressions in the form Euler found for evaluating P of n, and he wanted to show this is never positive. It's always negative or zero. And so, if we could move on, the next slide is a picture of Mărcă, and it's Xeroxed sufficiently badly that it could be anybody. So let's move to the slide after that, namely this slide. So we're able to prove this. If actually we had been clever, moving to the bottom of this slide, we could have proved the identity that you see on the slide right in the middle of the screen there, but we weren't clever, which means that we moved to the next slide, and we took an old formula of Euler that's in the screen, and this is what we discovered, that the generating function for this difference of four values of P of n is actually the expression you see in the middle of your screen now. And the point of this is that after the plus 1, there's a minus sign, and then everything in the series is positive, so the minus sign, or non-negative, so the minus sign makes things negative. And once we had seen this, we were eventually led to the next slide, which shows that indeed, if you truncate this at any point where you have an even number of terms, as we had for the case k equal 3, then, or at k equal 2, then you get this sort of a series, which means that this thing alternates sign according to whether k is positive or negative, even or odd. And so when k is 2, k minus 1 is odd, you will get a minus sign. And when you move for k, so stay on the previous side just a minute, please. Good. All right. So the point is that by being able to prove this, we not only prove the sort of inequality that Mircea Mărcă originally wanted, we prove that anytime you have an even number of these terms in Euler's sum, you get a non-negative entry. But even more interesting than that is the idea that this truncation actually has a fully combinatorial interpretation, which moves us to the next slide. So to best interpret this last series, we require the Mex function of Frankel and Peled. And they wrote a paper called Harnessing the Unwieldy Mex Function. So what is the Mex function? MEX stands for is minimal excludant. And so the mex of a partition is the smallest integer that is not a part of the partition. The mex of a partition is the least integer that is not a part of the partition. So, moving on to the next slide, we find that this sum that America was looking at in the case k equal 2 is actually equal to the number of plus or minus, according to the sign that you see in front of the sum, is indeed m sub k of n, where mk of n is the number of partitions of n, where the first number that isn't a part of the partition is k, and all the parts, there have to be more parts bigger than k than there are less than k. And the best way to understand this is by an example on the next screen. When k is 3 and n is 20, you see that the calculation for these differences of p of n is a fairly large set of numbers, starting with 627. But once you add and subtract all the various values, what you wind up with is 7. And that says that the partitions of 20, in which the first missing number, a missing integer, is 3, and there are more parts larger than 3 than there are smaller than 3. There are exactly 7 such partitions, and you see them listed on your screen. So this theorem is, so to speak, something that has as its genesis the work that arose in the last year of Ramanujan's life. Of course, Ramanujan really paid very little attention to the combinatorial aspects of his work, which is good for the rest of us because it gives us lots of things to actually think about. These topics that I've just described for you leave a variety of open questions. So the first question is, could we actually explain combinatorially this sort of plus, minus, minus, plus, plus, minus sieving process that eliminates all the partitions except those enumerated by this mex idea? The second question that we have, which is on the next screen, is that this seems to be an example of something related to Jacobi's triple product. And so a natural conjecture is this, and within actually the last 2 months, this problem has at least been solved analytically. It's been proved that this is true by my colleague at Penn State, Asa E., by actually 3 people have effectively solved this problem just within the last few months, so that this is not really a new theorem. So let's move on to the next slide, because this slide is out of date. These 2 gentlemen, Guo and Zheng, did the next case, but the full generalization has been actually proved. But there is a question on the next slide that is important, namely, are there any implications for Mach theta functions? So I have a few further questions. Unfortunately, when I sent you the prints, okay. I see that I have, so this slide that you see here, which is not in the same order as the slides that I have in my own collection, so I fear that I will have to skip around a little bit. This is a further thing from Ramanujan's notebook that I have included. It is rather technical and detailed, but there is a general philosophical question. Many people have asked, how much did Ramanujan understand of what at the time that he worked with Hardy would be modern mathematical analysis, in particular the more recent aspects of complex analysis. And one of the things that would be under consideration as part of that more rigorous analysis, is the theory of entire functions. So for functions of a complex variable, these are functions that have no zeros except a pole or an essential singularity at infinity. So one of the formulas in the Lost Notebook is what you see at the top of the slide here. And he tells you various things about the relationship between this series and product. One of the most disturbing aspects of this formula is that when you set A equal to 1, the series on the left is the first Rogers-Ramanujan series, so you would expect the series on the right to look at something like that. It doesn't look anything like the product in the Rogers-Ramanujan series. So a very natural question. I don't want to examine the proof of this, which is intricate in detail, but I do want to point out that the right-hand side is an entire function product expansion, as we shall talk about in the next few slides. So let's move on to the next slide, please. So here's the idea behind entire functions. The most important property of a polynomial is that it can be expressed uniquely as a product of linear factors of the form that you see on the screen. In this case, A is a constant, P is a positive integer or 0, which is the degree of, or the 0 of the 0 at 0, and Z1, Z2 up to Zn are the points other than 0 at which the polynomial vanishes, multiple zeros being repeated in the set according to their order. Conversely, if the zeros are given, the polynomial is determined apart from this arbitrary constant multiplier A by this expression. Now, a polynomial is an integral function, i.e., it is an entire function of the type that it has a singularity and infinity, in this case being a pole, and but it does not have any finite singularities, and we naturally ask whether it's possible to exhibit in a similar manner the way in which an integral function depends on its zeros. So, if we move to the next slide, the answer is yes. This is the theorem of Hadamard, at least in the weak case. I don't want to get too technical. So this is Hadamard's weak factorization theorem. So if f is an entire function and the reciprocals of its zeros and absolute value as a series form a convergent series, then the formula for the entire function if the function at 0 is equal to 1, is given by the expression you see on the screen, which looks just like the formula we had for the polynomial. Indeed, it is the formula for the polynomial when the number of zeros is finite. And if we move to the next screen, the point is that what Ramanujan was doing was looking at the entire function Hadamard product expansion for this series related to the Rogers-Ramanujan identities. So a question is, how much did he actually know of entire functions? And if he knew nothing of them, why did he write this down? All we can say is that this is what we see. This is what he wrote down. He gave no explanation of it. It shows that either he had studied and understood Hadamard's theory and had applied it in this case, or that he had his own Ramanujan explanation of these things, which corresponded perfectly to Hadamard's theorem. To actually prove something like this, one needs to look at the polynomials that now you see on the screen. These are the previous slide, please. These are orthogonal polynomials, so their roots behave exactly the way one would like them to behave. And in the limiting case, one is able to determine the expansion Ramanujan had. That's all I want to say in the proof. And what I want now is to go to the next slide, which is now the beginning of Ramanujan building on ideas of Euler. So that what you see on this screen is all Euler. Euler, in his major work in the mid-1700s, was the first to study infinite series, first to study infinite products. And one of the things he discovered, which is on the screen here, is the fact that these three products are identical. And it's obvious, apart from convergence questions, that these are identical. The mid product is gotten from the first one by the simple algebraic manipulation of this quotient to use 1 plus q to the n. And the product on the right is gotten by canceling all the terms with even exponents in the product in the middle. So this is Euler's theorem on partitions. But Ramanujan saw something really interesting. If we move to the next slide, remember that these products are all equal to S of Q, and on this next slide we see an identity which is unlike anything I had ever seen before. In particular, the infinite series that is in the middle of the right-hand sides of these equations that involve S of Q. Basically, what you see is the function S of Q with a partial product, one of the partial products subtracted. Since there are two infinite products that are identical, Ramanujan takes the series and subtracts the partial product of the 1 plus q to the n, and in this last line he subtracts the partial products where you have in the denominator the exponents that are odd. Now, recent work has done so many examples of this that it sort of seems like something that must go back into somewhere in the 19th or maybe even the 18th century. There's no such thing. This is completely, when you first run into this, it is completely perplexing. And when I was studying the Lost Notebook, it took me years to find the first proof of these assertions. Eventually, other questions arose, and if we go to the next slide, there is a general theorem in complex analysis that it can be used to give proofs of Ramanujan's formulas and numerous other results. But the point here is that you take an arbitrary infinite series that converges inside the unit circle, this f of c, and if you find that the sum as n tends to infinity of the limiting value of the alphas minus alpha n converges, and furthermore, that the convergence of the alpha n to the alpha is sufficiently fast that even when you multiply that by n, the limit is 0, then you get the expression at the bottom of the screen, that the limit is c tends to 1 from the left of the derivative of 1 minus c times f of c is equal to this sum. This is, so to speak, a next generation beyond a famous result of Abel, which basically said that if the alpha n's tend to a limit, then if you take the derivative sign away in the last line, the right-hand side would just be alpha. So this is basically the next formula beyond Abel. And so one might ask, well, if Abel discovered this in the early 19th century, why has this theorem only been discovered as a result of trying to understand Ramanujan's Lost Notebook? The only explanation I have for the fact that this was discovered so recently, it's actually in a joint paper with Jimenez and Ono and me. The reason it's been discovered so recently is that most of the classical series do not satisfy both conditions 1 and 2. It is only when you get to the Q series, the Q hypergeometric series, that you find numerous examples satisfying conditions 1 and 2. So in the classical hypergeometric series, nothing satisfies 1 and 2, and therefore the conclusion of the theorem is not applicable. So it's something that probably he, did not consider. Obviously, one of the implications is, well, if Abel's theorem is at one level and the theorem for the derivative is at the next level, is there something more general? And for that we move to the next slide. And the answer is yes. The point is, if you look at the bottom of the screen here, you see that the pth order derivative is used now, and the point is that there is a theorem comparable to Abel's theorem that now it deals, in the case p equal 1 is the thing discovered in proving Ramanujan's formula, but Pedro Freitas, a Portuguese mathematician, and I, in a joint paper, proved this more general theorem, and it has a variety of applications. If we go to the next slide, we'll just listed a few of them. But again, you see, starting with a special theorem of Ramanujan, which looked completely outrageous and unusual, one winds up with, nonetheless, seeing some general theorem that is that follows. And this, I think, is one of the most important aspects of Ramanujan's work, is that it generally is never the final answer. It's often the beginning not only of further results, but of brand new theories. So that sort of covers the implications that I wanted to talk about. Obviously, I've been highly selective in my choices. In particular, I've often cited things that arise from my own work, so I hope you'll forgive me for that, but these are the things that have most vividly brought home to me the added implications of his work. I also do feel that his ideas, at least as we see in the sort of scribbled pages from the Lost Notebook that you saw earlier, suggest things about computational work and computer algebra work. And this leads me to the next slide. So this is a quote from Hardy, which I think tells us aspects of Ramanujan that are also valuable to learn from, different from his explicit mathematical theorems. Quote, his memory and his powers of calculation were unusual, but they could not reasonably be called abnormal. If he had to multiply two large numbers, he multiplied them in the ordinary way. He would do it with unusual rapidity and accuracy, but not more rapidly or accurately than any mathematician who is naturally quick and has the habit of computation. There is a table of partitions at the end of our paper. This was, for the most part, calculated independently by Ramanujan and McMahon, and McMahon was in general slightly the quicker of the two. And if we'll go to the next slide, this is a quote of mine in a chapter in my book on Q series that I wrote about Ramanujan. Sometimes when studying his work, I have wondered how much Ramanujan could have done if he had had Maxima or Scratchpad or some other symbolic algebra package. More often, I get the feeling that he was such a brilliant, clever, and intuitive computer himself that he really did not need these aids. So, moving on to the next slide, this is an example. This actually comes not from the Lost Notebook, but from one of his original notebooks, and I should add that this is not quite accurate because he had drawn a line through this and basically had crossed it out. Why had he crossed it out? He had crossed it out because it's false. But it's true if you expand both sides as powers of Q in Taylor series, it's valid up through the first maybe 15 or 20 terms, which is really quite surprising. But this is the sort of thing where what one deals with in terms of evaluating something like this is, for us now, it is easy to check a computation by this, utilizing the computer algebra packages that I mentioned. On the other hand, Ramanujan seems to have been able not only to think this might be true, obviously having done the first few values, but by drawing a line through it to make clear that his computational power was such that he was able to do at least as well as the computer in picking out that it broke down for as you took more and more terms. So that is just a brief comment that I wanted to make about Ramanujan. The last year of his life, when many of these computations that you saw from the last notebook were taking place, I think is best described and summarized by a quotation of his widow in an interview she gave, I think probably in the 1970s. She said of him, he returned from England only to die, as the saying goes. He lived for less than a year. Throughout this period, I lived with him without break. He was only skin and bones. He often complained of severe pain in spite of it. He was always busy doing his mathematics, and I add parenthetically, this often consisted of this intense and extensive computation. She says, I continue, that evidently helped him to forget the pain. I used to gather the sheets of paper which he filled up. I would give the slate whenever he asked for it. He was uniformly kind to me. In his conversation, he was full of wit and humor. Even while mortally ill, he used to crack jokes. One day he confided in me that he might not live beyond 35 and asked me to meet the event with courage and fortitude. He was well looked after by his friends. He often used to repeat his gratitude to all those who had helped him in his life. So this finally sets up my final statement, which is both basically, I'm going to quote from an article by Edward Shills, who was a sociologist at the University of Chicago, and wrote a paper that was published in the journal Minerva, which was titled, let's see, wait a minute, I have the title right here somewhere. Just a brief, here's the title. Reflections on Tradition, Center and Periphery, and the Universal Validity of Science, the Significance of the Life of Srinivasa Ramanujan. So I'm not going to take you through Shill's entire article. I will point out to you that he is radically at odds with many of the modern tendencies in sociological, psychological, and in general social science research. And here are four of the subsections of his paper. Ambivalent Marxism, an early forerunner of the denial of the universality of science. Second, sociologists' disregard for any questions regarding the validity of scientific knowledge. Third, meta-history is a denial of the possibility of truthful knowledge. And fourth, does every civilization have its own criteria of scientific validity? And basically his article is designed to be a refutation of that, and a significant component of it is based on his understanding of the work of Ramanujan. And I want to take you through, as this final portion of this talk, or the next to final portion, the things that Shills said. From thinking about Ramanujan, I have concluded that there are no territorial or social or religious or ethnic limitations on the validity of what a scientist discovers. The discovery of a scientist of one civilization or nationality can be received, assessed, and assimilated by scientists of any other civilization or nationality, assuming, of course, that the recipient scientist is sufficiently informed regarding the state of the subject and has the intelligence and scientific training to comprehend what is offered to him. Next slide. The mathematics which Ramanujan did in India could be assessed by British mathematicians of the highest order to the extent that they could retrace the steps which his intuitive powers had enabled him to leap over. It was not the Indianness of Ramanujan's mathematics which baffled the first British mathematicians, Hobson and Baker, whom he approached. It was their exceptional advanced originality. It required two mathematicians of the very highest quality, Rardy and Littlewood, to appreciate and to learn from and to contribute to Ramanujan's work. As the years passed and his notebooks have been studied, his mathematics have been interpreted, proved, and assimilated by Western mathematicians. I have not read any references to the specifically Indian character of Ramanujan's mathematics. His mathematics are mathematics, indifferently of the place and the circumstances of their creation. Next slide. Contrary to the romantic idea that tradition and genius, or tradition and originality, are invariably antithetical to each other, the opposite is the case. A tradition receives into itself the product of the exertions of individuals of powerful intelligence, imagination, courage, and sensibility. Genius takes its point of departure in tradition. It extends and elaborates what is given by tradition. It begins in tradition, it departs from it, and reaches destinations hitherto unreached. It begins in tradition, and its subsequent advances from tradition bear within themselves traits of its point of departure in tradition. It never cuts loose from them completely, however far it advances from its starting point. This accounts for some of the difficulties Littlewood encountered when he tried to bring Ramanujan's use of more recently developed mathematical methods up to the level attained in Europe after 1880. Nevertheless, the achievements of the genius take their place in the tradition, which becomes significantly modified, and I would add enriched, by those advances. Next slide. The intimate reciprocal relationships between genius and tradition are evident in the case of Ramanujan. He made a connection with some older, incomplete condensations of the tradition of mathematics developed in Europe. He retraced in his own way, and in ignorance of them, paths of the tradition which had already been traversed in Europe, and in other respects he shot well ahead of them, of the points reached by the movement of the tradition in Europe. It is unlikely that the tradition of Hindu belief in which Ramanujan participated steadfastly obstructed his advances from the tradition of mathematics which had developed in Europe. Ramanujan thought that the Hindu goddess in whom he believed had in fact inspired his mathematical advances. It seems to this outsider that the specific and mathematical traditions are alive and well in India. Long may they prosper. In reflecting upon and honoring the life and work of Ramanujan, one finds numerous themes to support the nobler ambitions of humanity. And Schill's point of view is one with which I concur. I believe that mathematics especially is a universal set of truths that are in effect independent of however our brains are put together, and that each of us in every possible culture, in studying mathematics as it arises in the culture, the truths that one finds out in one culture are the same truths as in another. I want to close this talk on Ramanujan with one of my favorite passages taken from Watson's presidential address in discussing the work on Mach theta functions by Ramanujan. Remember that when Watson wrote this, he had only Ramanujan's last letter to Hardy to study. It would be 40 years after this that the Lost Notebook would come to light, and we would see how much more Ramanujan had learned. But he sent enough hints to Hardy that it inspired Watson's papers and this final statement, quote, "The study of Ramanujan's work and of the problems to which it gives rise inevitably calls to mind Lomé's remark that when reading Hermite's papers on modular functions, on a la chair de poule. I would express my own attitude with more prolixity by saying that such a formula as the one you see on the screen, which is quite amazing and is indeed an integral representation of a particular value of one of the Mach theta functions, gives me a thrill which is indistinguishable from the thrill I feel when I meet the Segrestia Nuova of the Capella Medici and see before me the austere beauty of the four shadows representing day, night, evening, and dawn, which Michelangelo has set over the tombs of Giuliano de' Medici and Lorenzo de' Medici. Ramanujan's discovery of the Mach theta functions makes it obvious that his skill and ingenuity did not desert him at the oncoming of his untimely end. As much as any of his earlier work, the Mach theta functions are an achievement sufficient to cause his name to be held in lasting remembrance. To his students, such discoveries will be a source of delight and wonder until the time shall come when we too shall make our journey to that garden of Proserpine where, pale beyond porch and portal, crowned with calm leaves she stands, who gathers all things mortal with cold, immortal hands. Well, this has been a talk in the evening, and I appreciate you coming out in the evening to hear a talk on Ramanujan. Thank you very much for your attention.